Okay, we're going to apply what we've learned here about exponential functions. Suppose 20 rabbits are taken to an island. The rabbit population then triples every half year. The function f of x equals 20 times 3 to the x, where x is the number of half-year periods, models this situation. How many rabbits would there be after 2 years? It's very important to understand what your input stands for and what your output stands for. So our input is x and our output is f of x. Now I'm going to rewrite the function that they gave us and I'm going to break it down. We have f of x equals 10 times, not 10, 20, 20 times 3 to the x. So this 20 represents the initial amount. So that's very important to know. That's your initial amount of whatever you're talking about. In this case, it's the initial number of rabbits. 3 is going to be our common ratio. So that's our tripling. So our tripling value. That means that we're going to multiply that value by 3, multiply by 3, multiply by 3. That's what tripling means. And then important to note that this x value right here, x stands for the number of half years. So 1 year would have 2 half years. 2 years would have 4 half years. So the number of half years. How many rabbits would there be after 2 years? So that means each year has a half year. 2 years means that I'd have 4 half years. So it's saying we need to find f of x when x equals 4. So f of x is going to equal 20 times 3 to the 4th power, which is 20 times 81, which is 81 times 2 is 162, and then we're going to add that 0 at the end. 1,620 rabbits after 2 years. So we go from 20 rabbits to 1,620 rabbits. So I knew it was going to make a triangle. Let's try this again. Close enough. No, that's not. Let's just get rid of all the box. Let's make a highlight, and it's going to be better. There we go. Look. That's not what I'm talking about. Hopefully you're laughing right now. Golly, she can't get a rectangle correct. There we go. Got the rectangle. So that means that, we start with 20 rabbits, and 2 years later we have 1,620 rabbits. This increases exponentially. And there are some really important things that are happening in our world right now in which we have exponential growth or potential of exponential growth. It's all around us. It was all around us many years before you were even born. So there's an exponential growth and there's an exponential decay as well. I want to come back up here and I want to define my variables, because if we can take a word problem and we can define our variables, that's going to be very important. Remember, we're very specific about the way we define our variables. X is going to equal the number of half year periods. And then our output that is dependent on the number of half year periods is our rabbit population. Our rabbit population, and you're really good at this, I know you are. Not just the rabbit population, but the rabbit population after X periods of time. Yeah, you've got that down, defining those variables. Okay, so let's try a problem. Suppose 10 animals are taken to an island, and then the population of these animals quadruples every year. I can even do this. look, I can choose my pen color, I can make it white, and I can white out this function right here, and I feel very confident you can come up with that function on your own just by knowing that we start with 10 animals and that quadruples every year. Let's start with defining our variables. What does x equal? What does f of x equal? That's our output. Write your function. I know you still have it on your note page. If you printed out the note pages, you've already got it on your note pages, and then let's look at how many animals there would be after 6 years. So go ahead and press pause, work this out, and come back, and I'll share my answer with you. Okay, welcome back. I got x equals the number of years that the animals are on the island. So the animals are on the island, whatever kind of animals those may be. And f of x equals, our output is our animal population. Animal population after x number of years. Excellent. Now looks like I'm writing on a slant there. I fixed that. So now we have our equation. F of x equals, our initial value is 10. And then our common ratio, that's our quadrupling, that's 4. And then raised to the x power. So that if x equals 0, they just got to the island, so x equals 0, that would be an output of 10. Because remember, if I were to put a 0 in, let's put a 0 in, we'd have 10 times 4 to the 0. Well, that would be 10 times 1, that would be 10. So that's how I check to make sure that I've got my exponent properly in my formula. We want to find f of 6. So we put a 6 in for x, 4 to the 6th power. 4 to the 6th power, I'm going to have to say, well, 4 to the 5th power, I know that from my exponent quizzes, that is 1024. And then I need to multiply that by one more 4. That would be the 6th 4, right? So 16, and then that's 9, and then 0, 4. So 4096, so 10 times 4096, that's going to be 40,960 animals after 6 years. Fantastic. So if you got that, then you're properly applying our exponential functions to real-world applications. You're doing a fantastic job. Let's look at graphing. We should know what the graph of y equals 2 to the x looks like because it's one of our parent functions, but if we don't know, that's okay. I'm going to show you what it looks like. So we're going to do some graphing, and we're going to do some more graphing, and then we're going to go back to some real-world applications with some exponential growth. So come back in the next video and we're going to do some graphing. Make sure you've got your graph paper because we're going to need it right here.